In question 10, we're asked to prove that if a normal process is white-sense stationary, then it is also strict-sense stationary. So first, let's take a look at the difference between the white and strict-sense stationary processes. For a white-sense stationary process, the expectation of the process is a constant number, and the autocorrelation T1 of T1 T2 should be the autocorrelation of T1 minus T2, so the difference. And for a strict sense stationary process, its statistics is not affected by a shift on the time axis. So that is to say, fx of x1, x2 all the way to xn, t1, t2 all the way to tn should be equal to fx of x1, x2 all the way to xn, t1 plus epsilon, t2 plus epsilon, all the way to tn plus epsilon. And that has to hold true for any n, any t1, t2, all the way to tn, and any epsilon, so any shift value. And now we know that x of t is a normal process. And that is to say, the density function fx of x1, x2 all the way to xn, t1 all the way to tn should be equal to this. So that is 1 over square root of 2 pi to the power of n times the square root of the determinant of c times this thing. And then c, which is the autocovariance, should be this number. So the expectation of x minus its mean squared, basically. So x is a vector, right? And then if we expand this expression, we have this. And then to just expand this matrix, we get this result. So each line, it would be the auto, so it would be like C, right? C of T1, T1, C of T1, T2, all the way to C of T1, Tn. And C is equal to the auto correlation minus the square of the mean. And here we have this eta number is because we already know x of t is a white-sense stationary process, and the expectation of this process should be a constant number. So we'll substitute all the e of x of t1 or x of t in general, replace them with this eta. And then we can see basically this matrix is what I just said, C of the difference between the two t timestamps, right? And here we can conclude this expression with this expression C of T1 Ti minus Tj when ij are both positive integers. And that is to say, the normal process, the density function of this normal process can be written as fx of x1, x2 all the way to xn, and then t, it would just be the two difference, the ti minus tj, when ij are both positive integers. And now we can have a look. If we put a shift value epsilon on every timestamp, so that is to say fx of x1, x2 all the way to xn, t1 plus epsilon, t2 plus epsilon all the way to tn plus epsilon should be equal to, also now we still have it would still have to be equal to the difference of the two timestamps. And we can see that the epsilon here just cancel out each other, and then we'll still basically have the same expression as here. And so that we can prove, after putting a shift value on the time axis, we still have this the same density distribution function. And so we can prove x of t is strict sense stationary.